Alrighty, in this video we are going to look at the fundamental theorem of calculus part 1. And as the name implies, there are multiple parts. There's actually 2 parts. So today's video is on the fundamental theorem part 1. Tomorrow's video will be on the fundamental theorem part 2. And then we're going to look at the relationships between them. So let's go ahead and jump in and just look at what this thing is. You've actually already seen this. But let me hit you with this one more time and give it its proper name as the fundamental theorem of calculus part 1, and then we will try to unpack this and look at a few different ways of understanding what this is actually saying. So what we have is the integral, the definite integral. Remember that this is a definite integral because I've got these what are called limits of integration, and indefinite integral does not have those. So I'm going from A to B, and I'm summing up an infinite number of infinitely thin rectangles, essentially. That's what this is saying, that have a height of f of x and that have a width of an infinitely small change in x. So an infinitely small width. And what this thing is equal to is the antiderivative of f of x, which we have defined as capital F of x evaluated between a and b, which, as you know, is equal to f of b, big F of b minus big F of a. This is the fundamental theorem of calculus part 1. So graphically, allow me to one more time just remind you what this is saying. We're looking at a to b, some function f of x, and what the definite integral allows us to do is find the precise area underneath this curve, which we are saying is equal to the antiderivative of b minus the antiderivative of a. So this is a little bit mind-boggling because if you kind of like remove yourself out of the out of the onion by one layer, and if you look at the graph of big F of x, this is, remember, our antiderivative. We're remembering that the derivative of big F of x is equal to little f of x. So keep that in mind as we look at this graph. The slope along this graph is how we define our function little f of x, which we've got right here. So if we look at these points a and b again on this function, what we're saying here is that the difference between this point, which is big F of b, and this point, which is big F of a, the difference between them, which if you take big F of a minus big F of b, remember that these are output values, these are y values, so if I trace this over to my y-axis and trace this over to my y-axis, this distance right here, that is what F of b minus F of a is on the graph of the antiderivative of little f of x, or in other words, big F of x. So you're finding some net change in the output values of the antiderivative, and what's crazy is that this number is the number that is the area underneath this curve. And this is mind-blowing. This is so critically important that it has this lofty name, the fundamental theorem of calculus. And in class we've looked at some geometrical arguments for why this relationship is what it is. But what I'm going to hope to do right now is give you one more argument that what I'm trying to do with this argument that I'm going to show you is to really get at the question. So this is the million-dollar question. Why does this work? Why does taking an antiderivative allow you to calculate the area underneath a curve? What is going on here? So let's go ahead and look at a function that we're going to call little f of x. This is going to look like so many of other pictures that we've drawn here. I'm going to pick some spot on the x-axis that we're going to call x. And let's go ahead and look at this shaded region. And I'm going to go ahead and assign a name to this. I'm going to call this a of x, which represents the area of this region. So this is the exact area underneath the curve of my function f of x. And then I'm going to pick another point a little bit beyond this thing, some distance h. Uh-oh. This might look familiar. So that means that this little point, this x value here, is at the distance, the horizontal distance of x plus h. And if I'm interested in finding the area of this whole region, so all of a of x plus this new little slice, that area is going to be a of x plus h. So let's pretend that I have a tremendous interest in finding the area of just this piece of the pie. This is what I want to find. I want to find the area of this thing. And let's let our imaginations run wild and say that this little distance here that I've called h, let's pretend that it's super, super tiny. Like infinitely tiny. What would I do if I want to find the area of this thing? Well, I would go ahead and take the area of the whole thing, which is a of x plus h. That's the area of all of this stuff. And then what I would do is get rid of all of this stuff, which I've called a of x. So that's a simple, the simple difference between a of x plus h and a of x. So for clarity's sake here, this is what we're finding is the area of the red chunk. A of x plus h minus a of x. Now the question is, what would happen if I took this area and I divided it by h? Let's think about this. If I took the area of this region and I divided it by h, we could look at a simpler example of just a regular old rectangle and say that this is base and this is height. And if I know that the area is equal to the base times the height, let's pretend that I divide both sides by b. I'm left then with h, right? And this is a little bit misleading because, well, it's confusing because I'm calling h a different thing here. Let's, well, hopefully you're tracking with me here. What I've got when I've got the area divided by the horizontal width of the rectangle is that I'm left with the height of that rectangle. And that's exactly what I've got going on right over here. If I take the area of the red chunk divided by the h, I'm left with the vertical component of this red region, which is infinitely thin. We were kind of, again, remember, we're letting our imagination run wild and say that this little addition of h is super, super tiny. So I'm left with a vertical component, and oh boy. And the vertical component anywhere along this curve is f of x, right? This is f of x, this is f of x, this is f of x. All these points, all these output values are f of x values. So this thing is f of x. So that's pretty cool. And now let's make this a little bit more mathematically precise and remind ourselves that we were letting our imagination run wild and letting h equal 0, but we can use symbols to communicate that with great accuracy, right? Because what do we know about? We know about limits. And so I can put a limit in front of this whole thing and allow the limit of this whole big thing, I can let the limit of h approach 0. That's what we're doing, right? We're letting this horizontal distance get infinitely small. So I'm hoping that as you look at this thing, you're like, oh my goodness, I know what this is. This is the limit definition of the derivative. And if I ask you, what is this the derivative of? Well, let me just remind you real quick. The limit definition of the derivative says this. The limit as h approaches 0 of f of x plus h minus f of x all over h. And what is this thing? This is the derivative of our function, which is f of x. This is f prime of x. Yes? Yes. This is the derivative of f of x. This is how we forged our understanding of what a derivative was. So if we go over here and we ask ourselves, what is the function here that I'm differentiating? Our function is the function a of x. What this whole big thing is a prime of x. So what I'm saying is that a prime of x and f of x are the same thing. A prime of x is equal to f of x. Whoa. All right, so what is this? What is this? Well, all right, let's remind ourselves what a of x is. What did we define a of x as in our picture? We said that a of x is the area underneath the curve in between 0 and x. This region has an area called a of x. All right, I got to make some more room here. All right, so a of x is the area underneath the curve. So what I'm saying when I say a prime of x, get this. This is nuts. I'm making this audacious claim that the derivative of the area underneath the curve of f of x from 0 to x is f of x. The derivative of the area is the original function. So I went through all this effort to try to convince you a little bit more of the fact that the derivative and the area under the curve, or the integral, are inverses of each other. The area under the curve and the derivative are essentially those operations that bring us to those conclusions of differentiating and integrating. Those are inverses of each other. They undo each other.